Hello, AP Stats. Okay, I want to go over one of the more difficult part of inference, which is understanding power and errors and how they are related when it comes to inference. When inference is used to make a decision, you either reject the null or you fail to reject the null. Those are your two choices. Sometimes we can think of fail to reject as accepting, but we're not really ever accepting the null, so keep that in mind. But sometimes when you're talking about errors, we kind of think about it as accepting in order to make it easier to describe possible consequences of making a mistake in our test. You can either reject the null correctly, or you can fail to reject it correctly, or you can reject the null or fail to reject it incorrectly. So rejecting the null incorrectly is called a type 1 error, and failing to reject incorrectly is called a type 2 error. So remember, type 2, null's not true. We failed to reject the null when actually it was true. So here is a little box. A lot of times I'll see students draw this on their free response questions. It's a great way to help you out if you're getting confused about your situations or if you're asked to give a consequence of a type 1 and type 2 error. So here are your options. Either your null is true or it's false. And you're going to either reject or not reject, fail to reject. So no, you have two possible correct decisions. If you fail to reject it when the null was indeed true, that's a correct decision. If you reject it when the null is false, that's not only a correct decision, but that's the decision that we set up the test for in the first place. We are trying to reject the null when the null was indeed false. So this is what we call the power of the test. The probability that we will reject it when we should have rejected it. Now the probability of a type 1 error rejecting when we should not have is called alpha, which we've seen before. Now that should make sense. If we are going to set our alpha, our significance level, to 5%, that means our probability of rejecting the null is 5%. So that's also the probability of making an error, rejecting when we should not have. If 5% is the probability to reject, then that's also the probability then we'll reject incorrectly. Type 2 error, the probability of type 2 error is called beta. Now alpha can easily be found. We're going to usually set it at a value at the beginning, and so therefore the probability of type 1 error is easy to find. But beta is a little more difficult because it totally depends on what the true value of the parameter is, what the true mu is or the true p, and we don't always know that. So therefore power, the probability, is going to be 1 minus beta. So these two are obviously inversely related. Type 1 and power go in the same direction. If one rises, the other one rises. That's good to keep in mind. So let's give it some context. We all know the story of the little boy that cried wolf, and the villagers put him out to look for a wolf, and he thought it'd be really funny to yell, "Wolf, wolf, wolf," and all the villagers feared there was a wolf and came to check on the poor boy, and of course there was no wolf. And this happened over and over again until the point where there was a wolf, and he cried wolf, and of course nobody came. The poor boy got eaten up. So we're going to set our null here to be that there is no wolf. That's the status quo. We're assuming there is no wolf. And the alternative is that there is a wolf. So the null is true would mean there is indeed no wolf, where if the null is false, the alternative is true, there is a wolf. So what is our consequences? If we fail to reject the null, people are not going to believe that there is a wolf. And of course, if we reject the null, people do believe. So often you'll be asked, in this situation, what are the consequences? Describe a type 1 error and say the consequences. So I would think, okay, type 1 error. So type 1 error would be if when I reject the null of no wolf, and I say there is a wolf, And so what happens in that situation when there is actually no wolf and I scream wolf? Well, all of the people will be very angry. So the other possibility, type 2 error, type 2, null's not true, so there is a wolf is what I'm starting to think. Okay, there is a wolf, and if I've made an error, there is a wolf, but I said there was not one, so that's a problem because somebody's going to get eaten in that situation. Okay, so here's looking at the probability, and this is where it can be complicated. Here is our rejection region. We either fail to reject, I'm writing except here, or we reject the null. So this area here would be our alpha. So if I set that at 5%, for instance, that means the probability of rejecting the null is 5%. So if our p-value comes out to be less than 5, then we will reject the null. Now, it should make sense to you why that's also the probability of a type 1 error. Rejecting the null when perhaps I should not have. Now, if we have a set z-value, okay, let's look at a different example. Let's take the example we used for the proportion of water on the earth was 70%. And we got some p-hat that was more than 70% by throwing the ball and what we discovered. And so that's this p-hat here, and it gave us a z-score of 2.027, which is pretty extreme, so we could calculate the p-value and decide whether or not we would reject. Well, if we fail to reject, if the null is not actually true, there must be a true p that we just don't know about it. So perhaps the true p, the true amount of water on the earth, is 80%. Yes, I know that's not true, but just hypothetically. If the true p was 80%, then there's really a whole normal curve there that we can't see. So if I look, I'm rejecting on this side, and I'm failing to reject on this side. So if I fail to reject, when the true p is 80%, then I'm in this area right here. Because if the true p is 80%, I'm actually looking at this new curve. That's where my proportions, my p-hats really are. But if my true p is 80% and I get a p-hat of this value, then the probability that I will fail to reject when I should not have is actually this blue shaded area. That's what we call beta. And it's almost impossible, well, it is impossible to calculate if you don't know what the true parameter is. And so that's why we won't be calculating it in here, because we won't usually know what the true parameter is. Okay, so what have we looked at? This right here is alpha, the probability of rejecting. It's also the probability of a type 2 error. The blue is beta, the probability of type 2 error. So where is power? Power is to reject the null when we should have. So if we look, if the true probability, true proportion, of water on the earth is 80%, then we should have rejected the null. Our null was that the true proportion is 70%. And our alternative in this case was probably that it was greater than 70%. So if we got a p-value, a p-hat, here, when our true p was 80%, then power would be all of this probability here, also known as 1 minus beta. So that kind of shows how the two are related. So how are they related? To decrease the probability of a type 1 error. Well, since type 1 error is set at alpha, your significance level, the most obvious way is to decrease your alpha. If you want it less likely to make an error to reject by mistake, well then decrease your alpha from maybe 5% to 1% so it's less likely to reject. So you'd be less likely to make the error. Another way to do it is to increase the probability of your type 2 error. Now know that if you decrease alpha, you are increasing the probability of type 2 error. Know also the only way you can decrease both errors at the same time is to increase your n, because of course that decreases your variability in your sampling distribution, and that's going to make all your errors less likely to make because those whole shaded areas will be smaller. So to decrease the type 2 error, of course you can again increase n. You can increase alpha. So remember, type 1 and type 2 are inversely related, so you can increase alpha. To increase power. Power is directly related to type 1 errors. So if you want to have a better test, better likelihood that you'll reject when you should reject, then you want to decrease the probability of your type 2 error, which is decreasing beta, which is hard to think about beta, but we can increase the probability of the type 1 error, which of course we did by increasing alpha. Increasing n, again, will also improve power as well that you want improved. Another thing that's interesting and a little hard to see, but if I go back to this, and notice I have moved this curve this way a little bit. So we had p at 0.7, and we had this new p was at 0.8. Well, what if p was actually 90% water on the Earth? Yikes! Well, we'd be drowning first of all, but hypothetically, if your parameter is actually further from what it was hypothesized to be, what has now happened to my type 2 error? It has become smaller. And my power of this area, probability to reject when I should reject, has actually increased. So another time you will be asked about improving power, and if the true parameter, the true mean, this could be a mu equals something, is further from your hypothesized value, you will also increase power and decrease the probability of type 2 error that way as well. I hope this helped.